Okay, so the concept of related rates goes back to, it's related to our implicit differentiation concept. It's the reason why we had to do that part first. So related rates is now taking the derivative with respect to of a function with respect to time. This will cause you to include a dx dt for taking derivatives of x with respect to time, dy dt's, or d whatever dt's. If it's like a dr, if you have radius in there for r, an a in there for area, whatever it is. So for example, if we have the original function y equals x squared. When I do my derivative of that function, the derivative of y is dy dt. Derivative of x squared is our 2x, but now it's a dx dt. Again, last time we did not have anything going with the x, but that's because it was always with respect to x we took our derivatives. Here it's with respect to t, with respect to time. That's why for every single variable that's not a t, we must have a dy dt, dx dt, d whatever dt for that problem. So, right here we're assuming both x and y are differential functions of t, where y equals the cube root of x, or as I'm going to rewrite it for derivative purposes, y equals x to the 1/3 power. We're given these two scenarios. If x equals 8 and dx dt is 2, find dy dt. And then scenario B, if x equals negative 27, dy dt is negative 3, find dx dt. So for both cases I need to find my derivative. Derivative of y is just simply dy dt, because derivative of y is 1, so we have to have dy dt in there. And then derivative of x to the 1/3 becomes 1/3 x to the negative 2/3 dx dt. Now that I have this information, I can now go ahead and apply the problem. So for part A, x equals 8, dx dt equals 2, find dy dt. So it's like a simple algebra problem. Dy dt equals 1/3 of x, so 8 to the negative 2/3 power, times dx dt, which is 2. When you work this out, you will find your answer will come out to be a positive 1/6. Because 8 to the negative 2/3 power becomes 1/4. 1/3 times 1/4 is 1/12. 2 times 1/12 is our 1/6. Then for option B, same concept, only this time dy dt is given as negative 3. We're told x this time is negative 27. We want to use this information to solve for dx dt. So in this case, we need to evaluate the 1/3 times negative 27 to the negative 2/3 power. So this will come out to be, very nicely, a negative 1/27. Because negative 27 to negative 2/3 is a negative 1/9. 1/3 times negative 1/9, sorry, positive, not negative, sorry. It becomes a positive 1/9. 1/3 times 1/9 is 1/27. So we multiply both sides by 27, and we get negative 81 equals dx dt. So the hard part really is making sure you get the derivative correctly. Derivative of y is dy dt. Derivative of x to the 1/3 is 1/3 x to the negative 2/3 dx dt. From there, you're just plugging in and solving the problem. So you can do the same thing for example number 2. xy equals 8. You are going to go ahead and take the derivative to set up the equation, and then go ahead and solve for each particular case. So go ahead and work that out. Make sure you pause the video so you don't see what I'm going to do next, and then once you are done, unpause it, and we'll see how you did. Okay, so for this example, we'll find in part A, dy dt comes out to be 1/2, and then part B, dx dt comes out to be negative 7/8. Again, the key comes from solving the original derivative. Product rule, derivative of x is just dx dt, so that's why it's y dx dt. Plus x, derivative of y is dy dt, that's why it's x dy dt, derivative is 0. Now, if you notice we need both an x and y variable, but I only give you x or y for both problems. Well, no big deal. The original equation lets you find the other one. If x is 4, 4 times y equals 8, y must be 2. So I have y, I have dx dt, I have x, I need to solve for dy dt. So 2 times negative 1 plus 4 dy dt equals 0. When we solve that, that's how we're getting a half. And then same thing for part B. Here, y is given as negative 8. So if y is negative 8, x must be negative 1 for the product to be positive 8. So I plug in for it, y, x, dy dt, and I solve for dx dt. You get a negative 7/8 for your final answer for this particular problem. So some of these problems are just going to be straightforward. They give you the actual equations, and that's it. The rest of them are actually involve different geometric concepts. You need to remember the different equations or how different sides and whatnot relate to each other. So for example, pebbles dropped into a calm pond, meaning nothing is moving, causing ripples in the form of circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. What is the change in area for the radius is 4 feet? So, talking about change in area, they want to find a dA dt. So I should talk about how to find the area of a circle to use that to find the change in area. So the area of the circle we know is pi r squared. So I take my derivative. Derivative of a would just be dA dt. Pi is a number, so we leave it alone. Times derivative of r squared is 2r dr dt. So now I have everything I need. I want to find dA dt, so that's the unknown. Radius is given as 4. And the radius is increasing at a rate of 1 foot per second, so dr dt is 1. So dA dt equals pi times 2 times 4 times 1, which means in the change in the area is 8 pi. And because we're talking about areas or volumes or lengths, we need to have the proper units. If it's change in area, it's the units squared, so feet squared, per your time unit, which in this case is seconds. 8 pi feet squared per second. That would be the change in area for this particular problem. Pi is an exact number, so you want to leave it alone like that. If this is a multiple choice question on the AP test where there's no pi, it's all decimals, you then go ahead and feel free to do 8 times the 3.14, the exact value though. Don't just do 3.14. All your calculus actually has a pi button on it, so make sure you use that. There you go. Remember, areas will always be feet squared over units. Change in volumes will be feet cubed over unit over the time units. If it's a change in a length, a radius, change in a height, change in a width, stuff like that, it will be the length unit over the time units. So, air is being pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. So it's the change in volume being pumped in. Find the rate of change of the radius when the radius is 2 feet. So first thing I do is I got to work with the volume formula. Because we're talking about air being pumped in, we're talking about dV dt right here. So dV dt is 4.5. We want to know our r is 2. We want to find dr dt. So volume for a sphere is 4/3 pi r cubed. You will be expected to remember the different basic volume or area formulas. If it's a little more complex, they will provide it for you. So we take our derivative. Derivative of v is just simply dV dt. Derivative of r cubed is, so we have our 4/3 pi and then 3r squared dr dt. So I'm going to simplify this first. The 3's will cancel, so this becomes just simply 4 pi r squared dr dt. So my goal is to solve for r. Let's plug in. dV dt is 4.5. Our r is 2. We want to solve for dr dt. So what I'll have to do is I'll have to do 2 squared times 4 pi to get 16 pi. And then divide both sides by 16 pi to get the answer. In fraction form, if I were to leave it as a fraction, your final answer will be 9/32 pi. Because really 4.5 is equivalent to 9/2. That's why it's 9/32 pi. And then our units are feet per minute. If you did want to leave it as a decimal, your decimal equivalent is 0.0895, and then feet per minute. Entirely your call. I personally, again, prefer to leave it as fraction, so I would have left it like that. It's more exact than the round-off decimal. So again, the same thing. You're using the given information to go ahead and solve a problem. So for this one, we have an airplane that is flying on a flight path that will take it directly over a radar tracking station, shown in this figure below. S is decreasing the rate of 400 miles per hour when S is 10 miles. What is the speed of the plane? Well, again, S right here is this diagonal distance from this tip of the plane to the radar tower. And x is the horizontal distance it's flying until it gets to the 6 miles. So in order to solve for this, I need to talk about the general situation. I don't need to know about when s is 10 meters. Or it's 10 miles, sorry. Again, all the previous problems talk about the general formula that relates to the given information. Volume is 4/3 pi r cubed. Area is pi r squared. We didn't care about the actual values for radius or volume until the very end. Same thing here. So if you notice, this is a right triangle. How are the sides of a right triangle related to each other? Pythagorean's theorem, which would be 6 squared plus x squared equals s squared. That's what we want to work with in terms of finding our derivative. So when we take our derivative of this, well, this is a constant no matter whether you square the 6 or not, so that goes away, leaving 2x dx dt equals 2s ds dt. They give us the ds dt. It's decreasing at a rate of 400 miles per hour. We're given s is 10. The goal is to solve for the speed of the plane. Remember, dxt represents the change in x, how this is changing. That represents the speed in this case, because how this is changing in this direction is how fast the plane is going. So, what we want to do is we need to get x in order to plug in and solve this. Well, if I know s is 10, how can I solve for x? Back to the original equation. Well, we couldn't use the 6 squared for the actual problem. I can use it to solve for x. In this particular case, 6 squared plus x squared equals 10 squared. It's 36 plus x squared equals 100. X squared equals 64. X equals 8. So at the time s is 10 miles, x is going to be 8 miles. So now I can plug in 2 times 8 times our unknown dx dt equals 2 times 10 times our negative 400. So when we solve that, 2 times 10 times negative 400 divided by 2 times 8, we'll get a negative 500 miles per hour. The reason why the velocity is negative is because we're going in the leftward direction. We're getting closer and closer to our target, that's why it's a negative velocity. But if they want speed then, speed is a positive 500 miles per hour. Again, speed is always the absolute value of velocity. Velocity tells you direction you're traveling in, speed just tells you how fast you're going. It doesn't care whether you're going to the left, the right, up and down, west, east, doesn't matter. So that's how we solve this particular problem. We're going to be using a geometric concept, Pythagorean's theorem, to set up how we can relate x and s together, so I can then go ahead and take my derivatives. The key is to always use the information given to set up an actual problem. So for this one we have a conical tank, vertex pointing down. So we have a cone. Vertex pointing down. There's 16 feet across the top and then 24 feet deep. Water is flowing out of the tank at a rate of 5 feet cubed per minute. Find the rate of change of the depth of the water when the water is 12 feet deep. So if I just take a look at a horizontal cross section of this, this right here is the situation. Our entire depth is 24, and this radius right here is just half the top, which is 8. I need to find some way to relate the height to the radius, because if we're talking about volume of a cone is 1/3 pi r squared h. Notice, unlike all the other problems, there are 2 variables here. So if I were to go ahead and take my derivative, I would have to use a product rule, which means I'd have to use r and h, dr dt, and dht in the eventual problem. I don't want to make this more complex than I have to. So for problems like this where there are more than one variable causing you to have to use a product rule, you're going to want to find some way to solve for one variable in terms of the other. Now notice, at some unknown height, we'll have some unknown radius for this problem. Back to this. The overall height is 24, the overall radius is 8, but at any point in there, the height is just simply an h, the radius is simply an r. What we have right here is a similar triangle. If you remember back to geometry, we can relate sides to each other. So the overall height, 24, is proportional to the height at any point in the same way that the overall radius is proportional to any radius at a certain point. So when I cross multiply, I get 24r equals 8h. Now, they're talking about, they want to find the change in depth. They want to find dH dt. So that tells me I want to replace all my r's with h's, so I can actually solve for dH dt. So if I divide both sides by 24, r is h over 3. So I can use that in the original equation, 1/3 pi times h over 3 squared h. This will come out to be 1/27 pi h cubed. I now have the volume in terms of one variable. It is now much easier to work with. And the whole key comes from, with these conical tanks, from this concept right here, this similar triangle concept. The overall radius is 8, overall height is 24. Once I have that information, I know that they are proportional to the radius and height at any given point, by the overall height over the height at a point equals the overall radius at the radius at a point. We cross multiply, and then we solve for the variable that makes the most sense. If I want to find the rate of change of the radius at a certain point, I'd have to solve for h to replace all the h's with r's. Because I want dH dt, I want to replace all the r's with h's. So I now go ahead and take my derivative. dv dt is 1/27 pi times 3h squared dH dt. Which, when you simplify, dv dt is 1/9 pi h squared dH dt. I can now plug in all the information. Water is flowing out of a tank, it's flowing out, therefore the volume is decreasing, so dv dt is -5. Our h is given to us as 12. And we want to solve for dH dt. So the goal is to go ahead and simplify this problem here to solve for dH dt. You will eventually find that dH dt works out to be a -5 over 16 pi feet per minute, or as a decimal equivalent, -0.0995. And again, just a quick recap. The key for this problem, again, recognizing the volume of a cone is 1/3 pi r squared h. Recognizing we don't want to take a derivative when there's two variables in there involving a product rule, so you must find some way to relate r to h. We do that by going back to our original setup. The fact that I can set up the concept of similar triangles using the overall height proportional to the height at any point, and the overall radius proportional to the radius at any point. That's how we solve for r, to replace 8, to replace the r in there, so I get it all in terms of h. I then took my derivative, plugged in, and solved. Okay, one last problem. This is going to be a three-part problem. It's all going to be based off the exact same original setup. So, a ladder 20 feet long is leaning against the wall of a house. We're going to assume the house is perpendicular to the ground, because it's a normal house. 20-foot ladder. The base of the ladder is being pushed into the wall at a rate of 1 foot per second. So that's x, that's y. We want to know how fast is the top of the ladder moving up the wall when the base is 12 feet per second. Sorry, the base is 12 feet from the wall. So if I'm pushing it into the wall, that's our dx dt. And if it's going in, it's going to the left, that's a -1. The goal is to solve for dy dt for this particular problem. So I use the original setup. How is x, y, and 20 all related? It's Pythagorean's theorem. So x squared plus y squared equals 20 squared. So there's the setup, there's Pythagorean's theorem. I want you to go ahead now, I'm using the rules of related rates, go take your derivatives, plug in for the x value, which is 12. The y value you'll need to solve for, but you can plug x into the original equation to get y, and then find dy dt. So go ahead and pause the video while you work it out. Unpause it once you have an answer. Okay, so we took our derivative of x squared plus y squared equals 20 squared. We get 2x dx dt plus 2y dy dt equals 0. Now we need to plug in for x and y and dy dt to solve, x dx dt and then y to solve for dy dt. We know x is 12, we know dxt is -1. Well, what's y? Well, when x equals 12, we have this right triangle where I know two sides, so I can solve for the third. So 12 squared plus y squared equals 20 squared. I solve that to get y equals 16. So we plug in for y as well. When we solve this out, you'll get dy dt equals a positive 3/4 feet squared. feet per second. It makes sense it's positive. We're talking about the ladder being pushed up a wall. dy dt is going up. Up is a positive direction. That's why it's a positive value for dy dt. Now, make sure you have all this information saved. We're going to use the same information, the same setup, to solve other things. So we know x is 12, y is 16, dx dt is -1, dy dt is positive 3/4. Make sure you have it saved. Because now I want to find the rate at which the area of the triangle is changing when the base ladder is 12 feet from the wall. Same setup. X, y, 20. We know x is 12. We know y is 16. We know dx dt is -1. dy dt is a positive 3/4. Well, in order to solve this, we need to solve for the area. Again, can't plug in yet. How is area related to x and y? It's a right triangle. Area is always 1/2 the base times the height. So what we want to do here is, even though we have two variables, unlike example 6 with the cone, we have dxt and a dy dt. So there's no need to solve for one variable in terms of the other. So I just take my derivative. So dA dt is 1/2. Derivative of x is dx dt. X dt. Y. Plus the 1/2 x. Derivative of y is dy dt. So now we just plug in. We want to solve for dA dt. So dA dt equals 1/2 of -1 times 16. Plus 1/2 of 12 times 3/4. So when you work that particular problem out, you'll find that your change in area will become a -7/2. Since it's changed area, it's feet squared per second. So because it's -7/2, what it's telling us is as this thing is being pushed in at 12 feet, the area is going down. So maybe initially the area was going up when you did that, but now at this point, we've reached a certain point now, the area, change in area is now going down. So that's how we use the area equation with the other given information to solve this problem. One last one. Find the rate at which the angle between the ladder and the wall is changing when the base ladder is again 12 feet from the wall. So an x, y, 20. We know x is 12. We know y is 16. We know dx dt is -1. We know dy dt is positive 3/4. We want to again find the rate at which the angle between the ladder and the wall, so this angle right here, is changing when the base is 12. So we need to find a way to relate the angle back to the x and y values. Well, the angle means a trig function. X and y, x is opposite, y is adjacent, so that's tangent. So tangent of theta equals x over y. So this now becomes a very interesting derivative. Derivative of tangent is secant squared theta d theta dt. X over y is a quotient rule. Derivative of the top is dx dt times the bottom minus the top times the derivative of the bottom, which derivative of y is dy dt, all over the bottom part squared. So to solve for theta, d theta to achieve the change in the angle, d theta dt has to equal dx dt y minus x dy dt divided by y squared. And then we had to divide both sides by secant squared, but remember, secant squared is 1 over cosine squared. So I can really think of this as 1 over cosine squared theta times d theta dt, which means I need to multiply both sides by cosine squared. So now we need to know is, well, what's cosine of theta? I'm like, well, I need to actually find the angle to find that. Well, again, remember your different right triangle trig back from geometry. Cosine is adjacent over hypotenuse. So the cosine of this particular angle is the side adjacent, which is y, which is 16, over the hypotenuse of 20. which is a nice fraction reducing to 4/5. So, our change in angle will be dx dt negative 1 times y 16 minus x 12 times dy dt 3/4, all divided by 16 squared, times 4 squared over 5 squared. When you work this whole thing out, and we'll take a little bit to figure the whole thing out, when you work the whole thing out, you will find that d theta dt will come out to be a negative 5/4. In the units, since we're talking about angles, radians per second. Okay, just to back up 1 second, just to make sure everyone's perfectly okay before we're finished, we want to find a way to solve for, we need to relate theta to x and y. Since x is opposite and y is adjacent, that's why we use tangent of theta equals x over y. We then take our derivative, where derivative tangent was our secant squared, which in secant squared is 1 over cosine squared, rewrote as 1 over cosine squared. And then derivative the angle is d theta dt. X over y is a quotient rule, so we do derivative the top, dx dt times the bottom, minus the top times the derivative of the bottom, all over the bottom part squared. And then to solve for d theta dt, I must multiply both sides by cosine squared to bring it all to the other side. That's how we got this equation, then we just plugged in and solved. So those are related rates. There are many different examples we can go over. I mean, the video's long enough as it is. I'm not going to do any more. Pretty much all comes down to how you remember your rules of geometry. How areas are related, volumes are related, how you can use right triangle information to solve for pieces. Anything at all, you need to remember how to use that information. Because once you have the general equation, you're going to use that to go ahead and solve, to take your derivative and then solve for the necessary d theta dt, dx dt, dr dt, dA dt, dv dt, whatever it happens to be. Okay, this concludes our unit on the basics of derivatives. There are more derivatives we're going to talk about in the next units. They're more complex ones involving natural logs, exponential functions, inverse trig functions, stuff like that. So I will see you next time.